made increasingly clear. It's about conflict and competition too. And so what I'd like to do today is to lay out the current status of the chip war, what it means for companies, but also how governments are thinking about the semiconductor industry as the world's largest economy, as the world's most important geopolitical players try in real time to rework semiconductor supply chains with profound implications for the world's technology sector. If you ask yourself how the world's key AI models are trained, or even better, if you ask the AI models themselves, they'll tell you a lot about model architectures, about algorithms, about the data on which they're trained. And all that is, of course, very true, but undergirding all artificial intelligence, the models as they're being trained, and even more importantly, as they're being deployed, is an extraordinary quantity of computing power. Semiconductors have been at the core of all of our advances in artificial intelligence. And today, as countries race to deploy AI as rapidly as possible, access to the most advanced chips is as significant as ever. And that's because undergirding AI progress, not just over the past couple of months or years, but really over the past couple of decades, has been the relentless march forward in semiconductor capabilities. Here's an extraordinary chart from a group of researchers that track the most advanced AI systems of their day, from the 1950s all the way up to the present, and added up how much computing power was used in the training and development of these AI systems. And on the vertical axis, you'll see it's exponential in scale rather than linear. And the chart shows us that to train each generation's most advanced AI system, we use exponentially more computing power, a rate of increase that is unparalleled in almost any other segment of the human economy, and is only made possible by the extraordinary progress of Moore's Law in providing more computing power that these AI systems require. And what's more, over the past 15 years, as we entered the deep learning era, the amount of computing used to train AI systems has increased at an even more rapid rate. In other words, it wouldn't be too much of a simplification to argue that the primary reason we have the artificial intelligence capabilities that we today take for granted are because of more and more advanced semiconductors that make it possible to train them and deploy them. That was something that was far from front of mind for most people just a couple of years ago, but today is a new facet of the chip war, a central facet that is making a focus for governments, but also for companies as they try to stay on the technological frontier. Other researchers have tried to calculate what's the share of progress that's come from algorithmic efficiency in artificial intelligence versus a simple application of more computing power. And what they find is that the application of more computing, the harnessing of more and better semiconductors to train AI systems, is vastly more important, and has been vastly more important for the last decade in explaining progress in AI. In other words, another data point of the centrality of semiconductors in building and deploying AI systems. This is what academics have found when they've studied trends in artificial intelligence. You don't need to only look at the academic literature. You can just follow Sam Altman on Twitter. Because once every couple of months, he's forced to tweet his apologies to ChatGPT users that he's got to restrict access to certain OpenAI features because, as he says, we don't have enough GPUs. We're working to get more, and we need more to deploy at scale the capabilities that are theoretically possible, but difficult and expensive to deliver to thousands, now millions of users on a regular basis, and he's not alone. In fact, all of the world's technology leaders, the leaders of the world's most important AI startups, the leaders of the world's biggest tech companies, have spent the last 3 years acquiring extraordinary volumes of some of the most advanced chips, and betting, in a lot of ways, their future on access to the most advanced semiconductors. In other words, it's not just academics who think that access to advanced chips is critical for deploying AI systems. It's the world's technology titans, too. And that's intersected in an interesting and complicated way with how governments view the explosion of interest in AI. Because of course, before Silicon Valley even existed, governments realized that semiconductors weren't simply important for developing consumer products or enterprise applications. They were important for military power too. As I illustrated in Chip War, the first chips that were invented were deployed in defense applications. And the guidance computer that guided the Apollo spacecraft to the moon, or the guidance computers like this one pictured here that guided intercontinental ballistic missiles from one continent to the other. And since the origins of Silicon Valley, there's been a deep interconnection between defense and security applications and the role of the semiconductor industry. And over the past couple of years, that has become a much more complicated relationship to balance, as companies have bet even more heavily on chips and the types of AI capabilities they enable. And as governments have looked at the shape of the semiconductor supply chain, focused today almost exclusively on consumer and enterprise applications, and tried to reshape it in a fashion that they could more effectively control. And so just like Sam Altman, who believes that access to the most advanced semiconductors and those cutting-edge AI capabilities are critical to his business and his future, so too, if you listen to national security leaders, they say the exact same thing. Here's the director of the National Geospatial Intelligence Agency, the part of the US government that uses satellites to take pictures and understand what's happening on the ground, quoted in public last year. It's integrating, he said, state-of-the-art computer vision and AI capabilities into analytic workflows that automatically detect, identify, characterize, extract, and attribute features and objects in imagery and video. And none of this is at all surprising. We use AI for this all the time. Computer vision capabilities are already widespread in the civilian economy, but they're critical to defense and national security too. And as governments have realized this, not just the US government, but other major governments as well, they've wanted to ensure they have access and even control over the most advanced semiconductors, which has pushed them increasingly to intervene in the shape of semiconductor supply chains, to try to refashion the ways that semiconductors are designed and produced in ways that right now are having a dramatic impact on how businesses have to make decisions. Governments today look at the question of AI infrastructure provision as critical to the national security. Where data centers are built, who operates them, what types of AI capabilities do they enable? From the perspective of leading governments, this is central to their future sovereignty. Many political leaders, from India to Britain to Japan, have articulated AI sovereignty as an important national priority. And when they use phrases like that, they're thinking of what are the data centers in their country? What are the chips operating inside? This is a priority of almost every major economy. And as a result of that, the question of access and location of advanced chips in the data centers they operate has been a central focus of key political leaders around the world. It's now a discussion point when world leaders meet and negotiate. And it speaks to the way in which governments are making themselves much more involved in the chip industry than they've been now for many years. And the problem, or the challenge that governments face, is that the chip industry does not at all map onto national borders. Governments are used to regulating and controlling and dictating what happens inside of their borders. That's how legal systems operate. That's how political systems are structured. But for now, over half a century, we've built a chip industry that does the exact opposite. That transcends borders, that stretches across different continents, that's been based on the concept of fairly free trade, low tariff barriers, now for many decades. And so today, it's hard to find a semiconductor that doesn't involve inputs, whether it's software, or materials, or chemicals, or manufacturing processes from multiple different continents, from Europe, from the United States, from Japan, from Korea, from Taiwan, from China. The chip industry operates one of the most multinational supply chains of any that exist. Indeed, it's hard to think of a product that requires a more multinational supply chain. Both because chips are extraordinarily expensive, requiring capabilities that you can often only source from a couple of countries around the world, and because there are so many process steps in their manufacture, dozens of types of chemicals, many different tools and inputs, that it's simply impossible for any country to go it alone. And so this mismatch between political leaders thinking about their own borders and an industry operating in a world that long felt borderless is shocking, I think, the system, is causing a reworking of supply chains, and we're living through that in real time. It's often that you hear political leaders in China, the United States, and the European Union talk about self-sufficiency, talk about the need to produce everything domestically, talk about supply chain resilience and think that the solution is to do it all at home. But when you start looking at the structure of the chip industry and divide it by each of the supply chain steps, as researchers at Georgetown University did here, what you find is that there's not a single country in the world that is anywhere close to self-sufficiency when it comes to manufacturing advanced semiconductors. Start with the EDA software tools that are used to design chips. Well, there's only a handful of companies that play a critical role in their design, mostly in the United States. But when you go to the next section, the production of intellectual property that's used in designing chips, well, there's the United States and Europe that play a central role in that process. What about the wafers themselves, the ultra-purified silicon wafers on which chips are made? Well, here too, you find that there's only certain countries, certain regions that can produce these wafers at the relevant levels of quality and at efficient prices, and they're not the same countries that have specialized in the software or the IP. Go down to the next step, the production of the tools that are used in semiconductor fabrication. Some regions have them, some regions don't. When you dig even deeper into this segment, you find that certain types of tools are only produced in certain regions. And when you begin breaking down the percentages of each segment that exist in each region, you immediately realize why self-sufficiency is going to be extraordinarily complicated, if that indeed is political leaders' goals. But resilience is something different. Resilience in terms of having supply chains that are trustworthy and secure and give you the supply that you need, that's an achievable goal. And over the past couple of years, I think we've seen many governments in Asia, in North America, and in Europe, when confronted with the realities of a supply chain that is this complex, begin to realize that self-sufficiency isn't something they're able to achieve over a realistic time horizon at a reasonable cost. And instead prioritize more resilient supply chains with backup options, with alternative suppliers, as something that they can plausibly achieve. And the reason they draw that conclusion is because replicating every step of the supply chain would not just cost billions and billions of dollars and take years and years to accomplish, it might well be impossible. And why is that? Well, look at tools like this. This is just one of the tools you need to make an advanced semiconductor, an extreme ultraviolet lithography tool. It wasn't so long ago you couldn't find hardly anyone outside of the Netherlands who could pronounce the phrase extreme ultraviolet photolithography. But today, when world leaders meet the Prime Minister of the Netherlands, it's often on the agenda. If you look at the readout of the last conversation between Chinese Chairman Xi Jinping and the outgoing Dutch leader Mark Rutte, they talked explicitly about tools like these. And because tools like these are often produced by a couple of companies, or in this case, just a single one, it illustrates how difficult self-sufficiency would be. And once you start digging into the supply chain for just a tool like this, you realize that even these tools require a multinational supply chain of their own. Hundreds of thousands of components, many of which can only be sourced from a couple of companies, some of the key components of which can only be sourced today from one company. Illustrating both the dependencies, but also the interdependencies that the chip industry was built on. Interdependencies that have driven efficiency, that have made possible ever more advanced technology, that have reduced the cost of computing, that have made possible artificial intelligence. But interdependencies that also make political leaders very uncomfortable because they require crossing national borders in ways that political leaders are naturally not accustomed to. And indeed, when you look at the supply chain, you do find certain areas of dependence that are quite striking. If you look, for example, at the production of many of the key minerals that are required, or materials in chip making, you find that whether it's the refining and processing of gallium and germanium, there's a whole lot that happens in China. 90% of certain types of materials are refined today in China, a level of market share that's been used repeatedly to try to drive up prices and create shortages abroad. And if you look at chip manufacturing capabilities, you find they're highly concentrated in East Asia, which has, of course, made governments in the United States and Europe concerned about what might happen if there were a disruption to those manufacturing capabilities. It's not wrong to think about potential choke points in the supply chain. And in the semiconductor supply chain, there are a whole lot of them. Many capabilities that are produced by just a couple of companies and a couple of critical capabilities that are produced only by one. And so thinking about choke points is absolutely central, especially because when it comes to the most important choke points, they're in most cases more severe today than they were 3 years ago when I published Chip 1. We've actually had increasing concentration in many of these cases, which has driven even more concern about how do you actually deliver supply chain resilience. Supply chain resilience matters not only because ChatGPT depends on it, or because AI models depend on it, or because building out big data sets depend on it. It's also because AI is already being deployed. The advanced computing capabilities that we rely on are already being deployed in pretty much everything. Look at the auto industry. You've got autos driving on the roads of the United States for a century now. But today, if you look at estimates of the chips going into cars, the fastest growing segment is chips used for autonomous driving capabilities. That's AI in practice. Not in the most cutting edge of industries, but in a legacy industry that employs tens, hundreds of thousands of people, produces products that are absolutely critical. The same is true in basically every segment of the manufacturing industry. Applying autonomy is something that's already happening. It's what we're living through right now. And so the resilience of semiconductor supply chains is important, not just because tech companies need semiconductors. It's important because as we learned during the pandemic, and have since forgotten, I think in many cases, the rest of the economy does too. It was only a couple of years ago that we were seeing regular news stories of auto companies having to shut down their factories because of a couple of semiconductors that they couldn't procure of the 1,000 that might be found in a new car. But the moment those headlines were no longer being regularly displayed, most of the country, most of the world put supply chain resilience at the bottom of their priority list. It's easy to forget about when it's not a priority. But when you look at the reliance of the entire economy, our entire manufacturing base, on access to growing numbers of semiconductors, this is an absolutely central concern. And it's going to become more important, I think, as time passes. More important because AI will be deployed in more devices. Look at the cost of AI over the past couple of years. It's collapsed. Nothing else collapses in prices as rapidly as AI has collapsed over the past couple of years. And when things get cheaper, we use more of it. And that's certainly going to happen with artificial intelligence, which means that we'll need even more semiconductors and even more devices to add intelligence to more products. That means even more industries will have to think about the resilience of their semiconductor supply chains too, which means that the choke point dynamics that I laid out in Chip 4 will become increasingly relevant, not just to companies in Silicon Valley, but to manufacturers around the world. And governments get this. They get this because they're looking at the same trend lines. They get it because when they listen to tech CEOs, whether it's Sam Altman or the DeepSeek CEO, they say the same thing. They say our most important challenge is acquiring the computing power that we need and deploying it at scale. And so long as tech companies keep saying it, governments will keep listening. And what's more, governments are realizing that for every advanced chip you need for AI processing, you're going to need even more less advanced chips to undertake all of the sensing, all of the communications, all of the other capabilities you put around an advanced chip. Here's phones. By one estimate, 96% of the chips in a phone or semiconductor devices in a phone might be lagging edge. The same basic dynamic is present in cars. Cars will have a couple of leading edge semiconductors managing the autonomous driving features, but even more lagging edge semiconductors. And the more intelligence we put in more devices, the more chips we'll need, which again increases the importance of resilient supply chains. And as we put autonomous capabilities in more systems, security concerns will grow. We've seen this repeatedly over the past couple of years, as segments that one might have thought were far from the front of concern when it came to security end up on the front pages because of concerns about supply chain security. One of my favorite stories from last year was about an investigation into the cranes in ports, which, like many pieces of industrial equipment today, are able to operate remotely and in some cases even semi-autonomously, which raises the question, what's your level of confidence about the components on these devices? Similarly, the Italian tire company Pirelli, which had devised a very impressive type of semiconductor that was able to measure tire pressure, found itself in the midst of a media storm when questions were asked, would this tire pressure sensor also let somebody understand where a car was driving to? If it was deployed at scale, what would the implications be for the security of your transportation system? Now, the location of my car on its own is probably not a critical national security concern. The location of every car in a given country, well, that's a valuable piece of information. And if all the cars were to stop at the same time, that could be a catastrophic event. And so governments look at the proliferation of autonomous capabilities, the proliferation of devices attached to the internet, and see both immense technological advances, immense scope for economic growth, but also immense possibilities when it comes to compromise and security, which is why we've seen in many key countries, the United States, China, and elsewhere, new restrictions on what you might think of as legacy sectors, because those sectors are being increasingly connected and increasingly autonomous. Auto sector, front and center. Last year, the United States began a process of restricting the use of components from certain countries in connected car capabilities in the United States, on the concern that certain components, if they couldn't be trusted, might introduce vulnerabilities. China has been reported has banned certain foreign cars from driving near military facilities, on the concern that they could be used for collecting signals, intelligence. And whether or not these particular concerns are true or valid, I don't know. What I can say is that we're hearing more and more about these concerns, more and more about supply chain security as it relates to connected devices, more about supply chain security as it relates to semi-autonomous action, which underscores the importance of thinking about supply chain security if you're designing a device that operates semi-autonomously, or even a device that simply connects to the internet. And what's striking to me is that this concern is not narrowing, it's growing, and it's growing rapidly. Just listen to senior US officials over the past couple of months. Commerce Secretary Howard Lutnick, just several weeks ago, said not only do we need to have semiconductors, we need to have flat panels that were made in trustworthy locations or even made in the United States. It wouldn't have been predictable over 5 or 10 years ago, the argument that flat panels were core to national security, but now there are many people in Washington who espouse that view. And the president himself tweeted just 2 weeks ago, in all caps, to make sure you paid attention, that the whole electronic supply chain was now a national security focus. Now, that is an extraordinary expansion of the definition of national security. And you might say it's excessively broad. It's expanded too far. Surely the chipboard doesn't need to be applied to every single semiconductor, every single electronic component that I own. And you might be right that certain political leaders have gone too far in expanding their definition of what counts. But I would note to you that President Trump is not alone in expanding the definition of where semiconductors intersect with national security. He's not alone among American politicians. He's not alone among Chinese politicians or European politicians or Japanese politicians. Every major economy is expanding the definition of what economic security and national security mean. And when semiconductors are involved, when autonomous capabilities are involved, when connectivity is involved, governments are increasingly defining that as security adjacent, which makes supply chain security even more central. And as this intersects with shifts in the global trading regime, like the tariffs that we're currently seeing, it implies dramatic changes for the way electronic supply chains are structured. Now, it took over a century to build the electronic supply chains that we have today, supply chains that crisscross the entire world, but especially the Pacific Ocean. And when you look at a single piece of electronics on the inside, you begin to understand just how complicated it's going to be to rejig the structure of supply chains, and just how costly a process this might be if undertaken too rapidly or without thought to efficiency. But I would point out to you that not only in Washington, but also in Beijing, officials are increasingly not only thinking, but also acting to tweak trade policy, to change tariffs, to implement rules of origins requirements explicitly designed to consider the nationality of every single component in a device like this, which for most of the last half century, companies have not had to think about. But today is front and center when political leaders think about supply chains and when companies try and often struggle to respond to them. You might not like this dynamic. You might dislike the cost associated with addressing this dynamic, but it seems to me part of a long-standing trend that governments are going to force companies to think much more carefully about the origins, the national origins of the devices that they're using. And the first part of my presentation suggested that defining even the national origin of a given piece of electronics is very, very hard. Where's a chip from? If it was made in one country but packaged in a second, designed using software from a third, that's not an easy question to answer. But governments are increasingly demanding that you find an answer to that question and imposing restrictions or imposing tariffs based on how that question is answered. In other words, I think the multinational supply chains that we've all grown up with, that the entire tech industry has grown up with, are increasingly being challenged by all of the key governments that are involved. And the latest round of tariffs from the United States are certainly a dramatic change, but part of a longer running trend that's been developing for some time. And it goes all the way up and down the supply chain, all the way to the lithography tools that are used to make chips, all the way to the minerals and materials that are used in the production process. Today, it's hard to find any step in the process that's been immune to political pressure to reshape how it's been produced. Which again illustrates the importance, the significance of understanding choke points. It also illustrates the need for companies to spend even more time thinking about supply chain security and the political challenges they face if their supply chain is not structured in a way a given government does. Because governments have found new and ever more intrusive ways to begin to shift supply chains. And you already see this happening in real time. The challenge, of course, is that governments can mandate, they can tax, they can impose tariffs and restrictions and local content requirements. But beginning to shift supply chains like this is extraordinarily time-consuming and expensive. A new chip-making facility can cost 2 or even 3 times as much as an aircraft carrier. And if aircraft carriers are slow to turn, well, supply chains are even slower to shift, which means that governments have to interact and consider the costs of the actions that they take. But what we've found is that the willingness to pay to reshape supply chains has grown steadily over time. Willingness to pay in China, in the United States, in other key geographies. And companies have had to adapt to this reality as they discover that governments are willing to put more resources behind supply chain reshuffling than they predicted. And the challenge for companies, for the entire chip industry, is to be responsive to the supply chain shift. It's unavoidable. Governments will keep putting restrictions and tariffs in place until they get the results that they want. But doing so in a way that doesn't compromise this chart, which of course Gordon Moore set out now over half a century ago, which has undergirded all the progress that I started my talk with. Because the risk of all these restrictions, all these tariffs, all of these local content requirements is that prices go up and the rate of progress goes down. And so the central challenge for the chip industry right now, I think, is to understand and respond to the demands for supply chain resilience and shifts, but to do so in a way that retains the efficiencies that have enabled such extraordinary progress. Now that's no easy task, but it's not just the chip industry that depends on it, it's all of human society, because there's been no more transformative feature over the last half century than the progress in Moore's law and the progress in semiconductor technology more generally. Progress that's enabled all of the tech companies we rely on and is driving forward artificial intelligence today, which is why we must ensure that the supply chain shifts that are happening and the further shifts that are coming happen in a way that's as efficient as possible and enable the technology that we depend on today and that we hope for in the future. Thank you very much for having me.